Hello, this is Tyler Beamer, math instructor, Haywood Community College. This is an instructional math video for Math 272. The purpose of this video is to take a look at infinite series. So this is Chapter 8, Section 3. So I want to go through some important definitions, proofs, and then look at some examples. So we've already talked about infinite series. Things to remember about infinite series is it is a series in which the terms of the sequence are added together. So notice that you've got this summation here. So essentially here's our sequence a sub k. So from k equals 1 to infinity, we're basically continually adding those terms. And then s represents the partial sum. So basically like s sub 2 is going to be the first and second term added together. S sub 3 is the first three terms added together, so on and so forth. So we can have partial sums of the infinite series, and we've already talked about that in a prior section. So here's the idea that we're working with, the main idea. So if the sequence of partial sums, S of n, right, so we can actually identify a function that would mimic the partial sum sequence, right? So if the sequence of partial sums converges, that is, if the limit as n goes to infinity of the partial sums equals L, then the value of the infinite series is also L, right? So essentially, if that infinite series continues to get added and added and added on to infinity, right, does that sum actually approach a finite value, L, which would be the limit? If that's the case, then not only does the partial sum converge to L, but the infinite series would also converge to L. If the sequence of partial sums diverges, then the infinite series also diverges. So if it doesn't actually converge to a number, say it just keeps getting bigger, bigger, and bigger, or smaller and smaller and smaller, then we would say that would diverge, and so would the infinite series. So in summary, to evaluate an infinite series, it's necessary to determine the formula for the sequence of partial sums and then find its limit. So that's how we determine the limit of an infinite series, is to essentially come up with the formula for the partial sums and then find its limit as it goes to infinity. So that's kind of the main idea of the entire section. Alright, let me and that was on page 619 in your textbook. This is on page 620, so you can obviously follow along in the ebook or the physical text, either one. So they give you this proof here on ways that we can find those limits. So we're going to first look at a geometric series, right? And we know that geometric series are series where the sequences are, or the terms in the sequence are found by multiplying. So geometric sum is basically the partial sum of a geometric series, right? So if I've got this summation here, right, here's my geometric sequence, right, geometric series A times R to the K, right? So if I basically continually take those terms and add those together, right, then that gives me partial sum of that sequence. So that's what that is describing. R is called the ratio, right, which we've talked about before. And R is important because that allows us to find the term that's getting multiplied over and over and over again. So here's an example, a geometric sum. So basically a partial sum of a geometric series where R is 0.1, A is 0.9, N equals 4. So you can see that this is what that would look like in the summation. Try to zoom in on that a little bit better. Okay, here's your ratio, 0.1. So that's at the base of this exponent k. A is this term here, which is the first term in the sequence. Okay, so if I plug k equals 0 into here, right, that's going to give me 0.9. So A is the first term in the geometric sum, or the first term in the geometric sum. So that's important to know. And so n is 4 because we start at 0 and go to 3. Okay, so if we want to find those first 4 terms, this is what that would look like. Okay. All right. So here's the proof that we're using. So here our goal is to find a formula for the value of the geometric sum, right? So here is what that geometric sum looks like in A and R's. All right, so remember A is the first term. We've got A times R to the first, so K would be 1 squared if K is 2, so on and so forth, to A to R n minus 1. Okay, so the first step that they do in this proof is to multiply both sides by R. Okay, and so that gives you this when we distribute the R through. Okay. And then the second part is to subtract equation 2 from equation 1. So this is equation 2. All right. This is equation 1. Okay. So essentially, if I subtract those out, these AR is going to cancel, AR squared is going to cancel, so on and so forth. So I'll be left with A minus AR sub n. Okay. And then on the other side, right, I am once again subtracting these two equations. So I've got R S sub n minus S sub n. So basically this is equation 2 subtracting from equation 1. So both sides are still equal. Okay. So then at this point, okay, we can rewrite this by factoring out an R, or I'm sorry, factoring out an A here. Okay, so if I factor out an A here, then I'm going to get, let me actually write this in. If I factor out an A, then I'm going to get 1 minus R sub n. Okay, and if I factor out of S sub n here, I get 1 minus R. And so if I divide both sides by 1 minus R, I get this down here. Okay. So that's a general formula for the value of the geometric sum. Right? So basically, at any point in the sequence of partial sums, if this is a geometric series, right? If I have A and R, I can find the value of that without having to continually find the previous terms and add them together. So that's what that formula allows us to do. Okay. So let me zoom out again. Whoa. And of course our goal is to find the limit. Alright, so basically where does that sequence converge to? That's the big idea. Alright, so that's what's being described here. Okay. Here's the geometric series. Right. Here's the geometric sum. Okay. Which we now said equals this. Right. So essentially, if n goes to infinity, right, does that geometric sum converge to a number, or does it diverge? Right. And so we actually use some of the previous work from a prior section to help us out with that. We already know that the limits, let me move this a little bit so you can see that. We already know that the limits for R sub n, or R to the n, sorry, are these with different values of R. So if R is less than 1, right, then we know that this is going to limit to 0. If r equals 1, this is going to limit to 1. And if r is less than -1 or greater than 1, then the limit's not going to exist, so it's going to diverge. So we essentially use that in our limit that we just found here for the geometric sum. So down here, we've got the limit, right, of s sub n, which is what we found earlier, right, which is here. Okay, so here's the first case. It actually says if r is less than 1, right? So the limit is dependent on the value of r. So if our absolute value of r is less than 1, right, then we know that this part, right, is actually going to limit to 0 based on this idea up here that we already know about. Okay. So that's going to, in essence, give us a over 1 minus r. So we can then use this to determine the limit of that geometric sum using the value of r. A is the first term, and then r is the ratio. So then we would know that it would converge to whatever this number is. Okay, so that's the first case. All right. Move this around some. All right. If r is greater than 1, right, then we know that the limit of r to the n power doesn't exist, right? So then we would not be able to find the limit of the geometric sum. So that would not exist. And then if r is equal to 1, right, then that would also diverge, right? Because basically you'd have the same number added multiple times, right? So then that would diverge because that would continually increase, right? So those three cases are really nicely put here in this theorem 8.7 for geometric series. So you probably want to use that, all right? So to find the limit, right, of the geometric sum, right, once again, here's the a over 1 minus r, and so if r is between 1 and -1, then we can essentially use this, right, because we're looking at the absolute value of r being less than 1, right, then we can use this and it would converge to this limit. If r is greater than or equal to 1, then it's going to diverge, right, which is basically what we just found in those three cases. So that's, in essence, the big theorem that we're using and the proof behind how we got there. Okay. So let's look at a few examples here in the book. Alright, so let's take a look at number 7 on page 623, and of course you can follow along here. Alright, so page 623, number 7. Okay, so it says to evaluate each geometric sum, and so these 7 through 18 on this page, they actually do not go to infinity. So we're not looking at finding the limit. We're just trying to evaluate this from k equals 0 to 8. So you can see that this is a geometric series here because we've got 3 to the k power. Our ratio would be 3, right? And a in this case would be 1. And we can find the geometric sum by doing the summation here of the first 9 terms. So we put 0 in for k, so that's our starting point here, and then we're adding that where we put 1 in for k, 2, 3, so on and so forth, all the way to 8. Okay. Alright, and then evaluate what that is. Alright, so that would be 9,841. So since that doesn't go all the way to infinity, we can find the exact value there. Okay. We should also be able to find that exact value using the value of S sub n from what we found earlier in the proof. Alright, so we know that A is equal to 1, we know that R is equal to 3, right? And I guess we're finding this for 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 values, right? So S of 9. Okay. So 1 minus 3 to the 9th. 1 minus 3. And we get the same thing, right? So this basically gives us this on top, -2 on the bottom, and of course when we divide, we get that same value. So this form, like we said, is really nice because then we can find the partial sum of any geometric series without having to find all of the previous terms. So that's what's very helpful about that. Okay. 13. Okay, we'll use S sub n since that's obviously easier. So we know that A is going to equal 1. That's the first term in the sequence. So if I put 0 in there for k, right, I'm going to get pi to the 0 power, which is equal to 1. And R in this case is going to be equal to pi. All right, that is my ratio. So I'm essentially going S to the 7th because we're going 0 to 6. So there are 7 terms there that I'm adding together. So 1 times 1 minus pi to the 7th over 1 minus pi, which of course is going to be this. If I leave it in terms of pi, if I multiply all that out, then I'll end up getting 1,409.835. So I'll have a decimal there. So this is obviously more accurate because we don't have any rounding error. All right. So those are 2 examples where you're just evaluating because this is not infinity, right? So we're actually going to a kth term, right? And we're not going all the way to infinity. So we're not really finding a limit there. Okay. And these next problems, we are finding the limit. Okay, so let's take a look at 19. See if this helps any. Nope. Okay. Alright, so the difference in these problems is we're actually going to infinity, right? So let's say that we just continually keep finding terms in the geometric series and then adding them together for the geometric sum, and we just keep doing that, right? We just keep going to infinity. So it's not like we just do the first 7 terms like we were doing here, or the first 9 terms like we were doing in these first 2 examples, right, where we had finite numbers here. The difference is we're going excuse me, all the way to infinity, right? So how do we figure out what that converges to, or does it converge? Does it diverge? And essentially, what is this limit, right? So this is where we want to identify the value of r. So this one's pretty easy. We know the value of r is 1/4, right? So if I look at theorem 8.7, right, r is definitely between 1 and -1 here, right? The absolute value of r is less than 1, so that would converge, right? And I'm going to use this idea to find that limit. So if I can identify a and r, then I can identify that limit. Right, so we know what r is, right? So a is the first term, right? So if I plug k equal to 0 into here, I'm going to get a equals 1. So now to find that limit, so the limit as k goes to infinity of the geometric sum equals 1 over 1 minus 1/4, which would be 4/3. So essentially, if k keeps going on and on and on and on, right, and I keep adding those terms together, it'll eventually converge to 4/3. Okay. All right. Let's look at 23. 23 is slightly different because you're given a partial sum. Okay. And then you're asked to identify the limit of the geometric sum. So the first thing is to essentially come up with a formula for the geometric sum. So if we have the first term, we know a, right? And then we want to identify what the value of r is, right? So if we take a look at this, r is going to be 1.01. Okay, and we can kind of test this theory. Here's what we're saying the geometric sum is. Basically 1 times 1.01 k. So if I put 0 in there, I get 1. Right? If I put 1 in there, I get 1.01 to the first. If I put 2 in there for k, I get 1.01 squared, so on and so forth. So that looks like that's correct. Okay. So then we want to find the limit of this, right, as k goes to infinity. Right. So what's going to happen as r gets larger and larger and larger, and I just add all those terms together, what's it going to converge or diverge? So in this case, we look at the value of r, right? That is definitely greater than the absolute value of 1. Therefore, we would know that this would diverge. So it's not going to converge to a number, it's just going to continually get larger. So we would not be able to find that limit. 25, they give you the geometric sum, so you don't have to find out what it is. Okay. However, it's not written in a perfect form for us to be able to identify A and R. Okay. So here's what I would recommend doing, is rewriting it. Right. So I can rewrite this as 1 over e to the 2k. Okay. Alright. And then I can actually use my rules of exponents to write this. Okay. And then I can rewrite this as 1, which is going to be A, right? That kind of like representing this one here, times 1 over e squared to the k power. Right? If I figure out what this is, right, that's going to be 1 to the k. Well, 1 to anything is going to be 1. And then on the bottom, e squared to the k power is e to k. Right? So that essentially rewrites this so that I know what A is and I know what the ratio is. Okay. Now in this case, k is not equal to 0. K is equal to 1. Right? So A is actually not going to be this number. I actually need to plug in this value of k to find A. A is going to be the first term. Right? So A is going to be 1 times 1 over e squared to the first. So that is equal to 1 over e squared, or e to the negative second. Okay. And then I have my ratio. I have my ratio R. R is 1 over e squared. And so we want to identify what that's equal to so that we can figure out what case we're looking at. So that's equal to 0.135335. So that is definitely less than 1. So then we can follow our limit formula that we have, which is A over 1 minus R. Okay, I have A e to the negative 2 over 1 minus e to the negative 2. Okay, so then we can rewrite this if we want to make these fractions, or to make the exponents positive. Combine the fractions in the denominator, and then essentially divide the complex fraction there, and you should get this. So then this geometric sum would actually converge to this number. All right. Let's look at 28. Kind of a similar problem. So 28 is geometric sum going to infinity. K equals 3. 3 times 4 to the k over 7 to the k. Okay. So once again, k is equal to 3, it's not equal to 0, so we'll have to plug that in to find a. But before we do that, we want to rewrite this so we can identify what the ratio is. So basically this is 3 times 4/7 to the k. And so that allows us to find what r is. So r equals 4/7. That's the ratio. We can identify the value of a, the first term, by plugging in 3. So that's 3 times 4 to the third over 7 to the third, which should be 192 over 343. So this value is definitely less than 1 here, right? So we can once again use the a over 1 minus r. To find this limit. So a we have here over 1 minus r. So we have 192 over 343 over 3/7. And then work with the complex fraction to get 64 over 49. All right. All right. 31. Actually, once again, gives you a sequence or a partial sum, infinite series. So then we want to first identify what the formula is for the partial sum. All right. So we know a is the first term, right? So we have that, which is 1 there. So if we think about what's happening here, right? Starting k equal to 0, 1 times e to the k pi to the k, right? If I plug 0 in here for k, all that's going to be 1 times 1, so that gives me the first term. If I plug in a k equals 1, the next term here, I get e over pi. If I plug in 2, I get e squared over pi squared, so on and so forth. We can rewrite this as 1 times e over pi to the kth power. So then we now know a is 1 from the first term of the sequence. We know the ratio, which is e over pi, and so we want to determine what the value of that is so that we can determine if it's going to converge. So that's 0.86525, which is definitely less than 1. So then we know it's going to converge, so we can then find the limit as k goes to infinity of the geometric sum which is going to be a over 1 minus r, which would simplify to pi over pi minus e. Alright. And finally, this one has a negative r, so let's take a look at that. 36. What's it look like? So k equals 1, negative 2/3 k. Alright, so we can identify A pretty easily. If I plug in k equals 1, that gives me negative 2/3, if I know that. And then R is equal to negative 2/3. That's pretty explicit. So we know that the absolute value of R is less than 1. Alright, so we're good there. So we can use the A over 1 minus R. So we've got negative 2/3 divided by 1 minus, 1 minus R. And of course those double negatives are going to turn to a positive. So we get negative 2/3 over 5/3, which is equal to negative 2/5. So that sequence, geometric sum, infinite series would converge to negative 2/5. Alright, so hopefully that'll get you started. Obviously you can read through the text on your own. There is another lecture video on MyMathLab. Feel free to watch that. You got all the help tools on the homework, and as always, if you have questions, email those to me or stop by the office. Alright, have a great day.